Find the electric field at point P, which is a distance a from the center of a thin line of charge of length L and uniform linear charge density. What is the electric field if A is much greater than L? Let's start by drawing the charge. So we have a line of charge, and this line of charge has a certain length, L. Being a line of charge, we can treat this charge as a one-dimensional object. Being a one-dimensional object, it only has length. It doesn't have width or height. So let's choose a coordinate system that reflects the geometry of this charge. A natural coordinate system to choose is a rectangular coordinate system. And in this rectangular coordinate system, let's put the x-axis parallel to the charge, where the charge lies right along the x-axis. And let's place the origin right passing through the center of the charge. So I will place the origin, the y-axis, crossing our charge right at its midpoint. Our goal is to find the electric field at this point P, and we know that this point P is a distance a above our x-axis. Here's the problem. We know how to find the electric field of a point charge. The electric field of a point charge we've shown is equal to the Coulomb's constant times the charge divided by the distance between the charge and the point at which you're calculating the electric field. The problem is this line of charge is not a mathematical point. It has a dimension, and that dimension is a length. So we cannot directly apply this formula for a point charge due to a line of charge because the formula doesn't apply. Yet, this is all we know how to do thus far. So the challenge for us is, how can we solve this problem using knowledge we already have? And the knowledge we have is we know how to find the electric field of a point charge. Well, this is how we do it. Let's take an infinitesimally small element of charge along this line. So let's take this piece of charge right here. Now this piece of charge is going to be at a distance x away from the y-axis. And this piece of charge is going to be a certain length. We will say it's a tiny bit of length along a tiny section of the x-axis. Now, this length differential or x differential, it is infinitesimally short. It is so short, in fact, we could model this tiny representative element of charge as a point charge. Since we're modeling this as a point charge, we actually know how to calculate the electric field of this tiny bit of charge. The electric field due to this tiny bit of charge is dE. And let's assume this tiny bit of charge is a positive charge. So this is why I drew the electric field vector pointing radially away from our representative charge element. This tiny bit of charge, let's say it's a tiny bit dq, where the total amount of charge is just q. So this is our infinitesimally small amount of charge that is infinitesimally short in length. So this is our point charge. For this point charge, we know that this point charge has an electric field given by the expression we found before. In this case, the amount of charge we're dealing with is the very tiny representative charge element. And that charge element is a certain distance away from the point we are interested in. That distance in this picture corresponds to the variable r. Well, we've gotten one step closer to finding the electric field due to this line of charge. This expression right here gives us the magnitude of the electric field due to this line of charge. However, we still need to determine the tiny amount of charge, dq. That wasn't given to us. And we still need to determine r. But before we get too far ahead of ourselves, let's go ahead and look at some other pieces of information that we have. Electric field is a vector. So this tiny bit of charge has an x component. The x component to this tiny bit of charge, I'll put right there. We will call this dE sub x. This tiny bit of charge also has a y component. We will call this y component dE sub y. Now you might be wondering, well, why do we need the components when we already have the formula for the magnitude of the electric field due to that charge? Well, one, we need the components because the electric field is a vector. We're going to want to know not only its magnitude, but we want to know its direction. And also because our problem says find the electric field for that line, not for the representative charge. In fact, we're going to take that representative charge and we're going to have to add up all of the tiny pieces along the x-axis. That means we have to add up this tiny piece plus this tiny piece, plus this tiny piece, and we're adding up an infinite number of these tiny pieces until we sum over the entire line of charge. Okay, so we're adding up a whole bunch of pieces, and right now you're probably thinking, well, integration might help us out, and you'd be right. The thing is, let's not do more work than we have to. We will need to integrate, but right now notice that we have both an x component of the electric field we have to deal with and a y component of the electric field we have to deal with, and we have an infinite number of those. So is there a way we could maybe simplify this problem so we do a little bit less work? Well, what I see here is for every representative charge element on the right side, we have one that is equally distant from the point on the left side. I want to use symmetry. The reason why I put the origin passing right through the center of the line of charge is I'm seeing that I could use symmetry to help me solve for the net electric field at point A. And in using symmetry, for every point on the right side, we have a mirror point on the left side that is the same distance to point A and has the same magnitude of charge. So the point on the left will contribute to the net electric field at point A. Since they are both positive charges, their x components are going to be opposite in direction. The x component, I'll just call this contribution on the left, I'll just call it dE sub L for left. What I'm doing here is, usually when a problem has some amount of symmetry, we could simplify it in some way to minimize the amount of work we have to do. Because for every charge element on the right side, there's a mirror element on the left side, I suspect that some component of the electric field will cancel. And when I sketch the components of the electric field of my charge, representative charge on the left, I see that its x component points horizontally to the right. And I also see that it has a vertical component to the electric field. I'll call that vertical component DELY. So if you look at this picture, the element of charge on the right let me rephrase that, the charge element on the left has a component of the electric field that points to the right. And that component of electric field that points to the right is opposite the component of the electric field that points to the left for the representative charge we started off with. What this means is the electric field due to the pair of charges along the x-axis will sum to 0. In other words, we don't have to calculate an x component of the electric field because the x component of the electric field ends up being 0. There's only a y component. Let's copy our graph to the next page. So we know there is only a y component left over. Since there's only a y component left over, I am going to just calculate the y component of the net electric field at point A. And you could see quite simply using vector addition that if I take that vector of our mirror image from the left-hand side and add it to its mirror image on the right-hand side, notice that we get a net vector that points straight up. There it is. That's the net vector that points straight up. So now that we know that we will only have a y component of the electric field left over, because of symmetry, the x component will sum to 0 because for every charge on the right, there's a mirror charge on the left. And since it's like charge and that mirror charge is the same distance, the x component cancels for this charge configuration, we're going to only be left with a y component. And since we are only going to be left with a y component, we are going to need to sum up all of the individual y components of our representative charge elements. So let's say we have n elements. So we have to sum up all of those n elements. And since this is infinitesimally tiny, we're going to have an infinite number of those elements. So in summing up an infinite number of tiny charge elements, we end up with an integral. So this is what we need to find. We need to find that integral of the electric field of the y component. And this is the y component of our point charge. Now that y component of the electric field can be expressed using some trigonometry. if we look at our representative electric field in our diagram, and let's call this an angle theta. That y component, being the side opposite that angle theta, is going to be given by the hypotenuse dE times the sine of the angle we've labeled in our picture. This means that the net electric field is going to be equal to the integral of dE times the sine of that angle. And dE, we said earlier, is equal to k dq over r squared, sine of the angle. So now we have a problem. We have an expression that has three different variables. The Coulomb constant K is just that, a constant. So we could write that outside of the integral. We don't have to worry about that. What we have left over is the charge Q. And this charge Q, well, really it's charge dQ. And dQ could vary. dQ, that amount of charge goes from the left end of the charge element, or of the line of charge, to the right end. So Q is a variable. Theta is a variable. Now, how theta is a variable is if you look back at our picture, here's our theta down there. But if you look at our picture, as you integrate, let's say we integrate a charge element that is over here. That charge element that's over there is going to have a different angle than the charge element here. And that charge element there is going to have a different angle, is going to have a different angle than a charge element here. So the angle theta is varying. And if you look at our diagram, all of those different distances vary as well. So r is a variable. So the task we find ourselves trying to answer is, how do we integrate this when we have three different variables? So we only right now know how to integrate with one variable unless you've had multivariable calculus. So this means we need to express either Q in terms of r and theta, or theta in terms of r and q, or r in terms of q and theta. And hopefully we can express those maybe in terms of the same unknown. Maybe we express q in terms of r, or if possible in terms of theta. Maybe we express theta in terms of r, or if possible in terms of q. Or we express r in terms of q, or if possible in terms of theta. That's our task. Our charge element Q, remember, has a length of dl, which that infinitesimally small length is equal to dx because we are along the x-axis. We are also given a relationship between the charge element and the linear coordinate. This is a linear charge, a thin line of charge. And we know that the density for a line of charge is given as lambda. At least I use the variable lambda to represent linear charge density. Your book might use a different variable. So the linear charge density is defined as dq over dl, charge per unit length. This gives us the connection that we need between the charge q and the spatial variable, because upon rearrangement, we see that our representative charge element is equal to the density times the tiny amount of charge, and we set our coordinate system such that the tiny amount of charge dl lies along the x-axis. So we could say that the infinitesimally small representative charge dq is equal to lambda dx. To get the relationship between the variables, let's just quickly resketch our diagram. We have the charge along the x-axis. I will put the x-axis like this. The y-axis is passing right through the middle. We are interested in point A. The representative charge element is here. Here is our infinitesimally small electric field vector. This point that we are interested in is point A. And that point A is a distance r from our representative charge element. And that radial line, that line from our representative charge element to point A, is at an angle theta. And our representative charge element is a distance x from the y-axis. So if you look at this, we have a right triangle there. That right triangle has sides x, a, and a hypotenuse of r. This is enough information to express r in terms of x and a, and theta in terms of x and a. From this, we see that r from Pythagorean's theorem is equal to the square root of x squared plus a squared. From this, we also see that the sine of the angle theta, that's going to be associated with our y component, is equal to the opposite side over the hypotenuse. And for us, the opposite side is side A. The hypotenuse is the square root of x squared plus a squared. We now have everything we need to determine the electric field due to that line of charge. Let's look at what we have. We need to express the electric field in the y direction in terms of dq sine theta and r. Well, we don't need to express it. We've already expressed it in that. So let's just copy that here and start working with it. So the electric field in the y direction is equal to k times the integral of dq. dq we said is equal to lambda dx times sine of theta. Sine of theta is a over the square root of x squared plus a squared times r squared, the distance between the charge element and the point in question. R squared is just the sum of x squared and a squared. And then the only thing we have to do with this integral now is to figure out the limits of integration. If we go back to our picture, let's go back here. This charge is a length of L, which means from 0 to the right end of our charge, that's a distance of L over 2. I'm going to just go ahead and call L over 2 d. And the distance from the left end of our charge to the origin is L over 2 as well. So our limits of integration become minus L over 2 to L over 2 which I'm just going to call from minus d to d. Now we can also apply symmetry to the integral. Because remember, for every element on the right, we have a mirror element on the left. The integral is going to be symmetric. Since the integral is going to be symmetric, I could just multiply the integral by 2 and have the limits of integration go from 0 to L over 2. So this is 2k lambda a over x squared plus a squared to the 3 halves dx. This right here, once we integrate, will tell us the electric field due to that line of charge. Let's pull the constants outside of the integral. So we have 2k lambda a from 0 to d. I'm replacing L over 2 with d. 1 over x squared plus a squared to the 3 halves dx. We could look up the result of this integral in a table. It's a rather common type of integral to deal with, and if you're in a multivariable calculus class, we'd have you evaluate this out, maybe using a trig substitution. But in physics, we're going to just make use of an integration table. So in making use of the integration table, I know that this quantity right here, and actually, yeah, that quantity right there is going to correspond to x over a squared times x squared plus a squared from 0 to d. That's the limits of integration. And then we have the 2k lambda a on the outside. Putting in our limits of integration, I'll factor out the 2k lambda a. The first term is d over a squared. Oh, and I forgot the 1/2 up here. D over a squared times the quantity x squared. But wait a minute, we're plugging in the upper limit of integration, so that'll be d squared plus a squared to the 1/2. That's the first term. And the second term is 0 over that stuff because the lower limit of integration is 0. And so that term goes to 0, or not even goes to 0, that term is 0. So what we have then is 2k lambda a d over a squared times d squared plus a squared to the 1/2. We said that d is equal to L over 2, so the y component then is 2k lambda a L over 2 over a squared L squared over 4 plus a squared to the 1/2. We could simplify a little bit. An a in the numerator, we'll get rid of one of the a's in the denominator. A 2 right here gets rid of a 2 right there. And what we have here is the electric field in the y direction is equal to k lambda L over a times the quantity L squared over 4 plus a squared to the 1/2. So what do you think this quantity lambda L corresponds to? Well, lambda L corresponds to the total charge represented by that line. How do we know that? Well, we know that it is a uniform charge distribution. And remember, if it's a uniform charge distribution, dq equals lambda dl. If you integrate both sides, and lambda is constant because it's uniform, you get q equals lambda L, and that's what we have right down here. So the k lambda L is just the charge we have. That allows us to write the electric field in the y direction is equal to k q over a times the quantity a squared plus L squared over 4 to the 1/2. And since this is integrated over all the charge, and since we only have a y component for the charge due to this line of charge at the point A, we could vectorize this and say the electric field at that point A is kq over A times A squared plus L squared over 4 to the 1/2. And let's go ahead and say the electric field at point A by putting that in parentheses. And this is along the positive y-axis, j hat. Oh, that's great. That's awesome. Now, before we box our answer, let's just do a quick unit check to see if at least the units work out. Because if the units don't work out, we know we made a mistake somewhere. So the units of the electric field is a Newton per Coulomb. The unit of the Coulomb constant is the Newton meter squared per Coulomb squared. Charge Q has units of coulombs. A has units of meters. Inside the square root, we have an A squared and an L squared. So that's a meter squared, and that's in a square root. The meter squared in the numerator cancels with the meter squared in the denominator. a coulomb in the numerator cancels with one of the coulombs in the denominator, and we are left with units of newtons per coulomb. Now that we know our units check, we could box our final answer. This is the electric field at a point A along our y-axis. Let's give ourselves a reality check. So the reality check is kind of outlined for us in part B. Part B says, what is the electric field if the point A is much, much greater than the length of our line? So what do you think it means that A is much greater than L? Well, what it means is we are so far away, the size, the length of that charge doesn't matter. It's negligible in comparison to the distance. Imagine you're looking at something, and this object, maybe you're looking at a car. And when you're standing right next to the car has a size, the car has a shape. But as that car moves further and further away, it gets smaller and smaller and smaller. Eventually, the car will move so far away, it'll look like a dot in space. So if A is much greater than L, that's really saying we move so far away that the charge is going to look like a point charge. Well, let's discuss that differently. Let's look at that mathematically. So let's take the electric field. Let's look at the limit as A gets very big. So we will say as A will get much bigger than L. So this probably isn't correct mathematical way of expressing that, but that's how I'm going to do it, and I think you get my idea. So if we look at that, the limit of our electric field as we get farther and farther away, as A gets much, much bigger than L, let's see what it does to our expression. So if A is much, much bigger than L, in the square root, L is going to L is going to be negligible. Since L is negligible, we don't have to consider it in the square root. So that means since we are neglecting L, since A is so much bigger than L, what this becomes is KQ over A squared. But remember, the electric field due to a point charge, remember, is KQ over R squared, where R is our distance between the charge and a point in space, and R hat is representing a unit vector along that radial line. Well, what we have for this line of charge looks just like the expression for a point charge if the distance we are from the line of charge is much, much greater than the length of our line of charge. And if that's the case, this looks like a point charge just as we expected. If something is so far away that you could barely see it, it becomes a mathematical point to your perspective. It makes sense that mathematically the electric field looks like a point charge on this. And this should give us confidence. This should be one of our reality checks. When you do a reality check, choose something that you kind of know to be true or you would expect to be true, and see if your result matches that. And if it does, that gives you more confidence in your result. And if it doesn't match, then maybe your expectations are wrong, or maybe your calculations are wrong. At any rate, it offers a room for reevaluation and reflection. But for now, we should feel pretty good about this result.